In 2011, Adam Riess won the Nobel Prize for discovering the universe's expansion is accelerating. Years later, measuring that expansion again, he got a number that didn't line up with what the equations predicted. Then we built a $10 billion telescope, James Webb, to prove him wrong. It didn't. Webb looked closer than anyone ever had and made the problem worse. Something out there is telling us this isn't the universe we thought we lived in. Let's find out what. Here's what Riess actually found and why it mattered so much that a Nobel laureate's name is attached to it. Scientists have two completely different ways to measure how fast the universe is expanding. Method 1 looks at the deep past. It studies the cosmic microwave background, the leftover afterglow of the Big Bang, light that's been traveling for over 13 billion years. From the tiny patterns in that ancient light, scientists calculate what today's expansion rate should be: 67 kilometers per second per megaparsec. So how do you measure right now? With two kinds of stars that never lie about how bright they really are. Cepheids blink at a rate that gives away their true brightness. Slower blink, brighter star, no exceptions. Type 1A supernovae are even more reliable, exploding white dwarfs that always detonate at the same mass, like a bomb built to the exact same spec every time, so they always release the exact same amount of light. Know how bright something really is? See how faint it looks from here. The gap between those two numbers is a distance. This is Riess's method. Work out the distance, measure how fast the galaxy is racing away from us, and divide. His result, 73. 67 versus 73. A 9% gap. And how sure are we this isn't just sloppy measurement? Both numbers are precise to within 1.5%. Statisticians call the gap a 5 sigma result. Under a 1 in a million chance, it's random noise. That's the same bar of proof physicists demanded before they'd say, out loud, that they'd actually found the Higgs boson. Riess didn't quietly file the result away. He and his team kept measuring, kept refining, and kept getting the same uncomfortable answer. Scientists gave the discrepancy a name: the Hubble tension. Not everyone thought that name was strong enough. At a 2019 conference at the Kavli Institute for Theoretical Physics in Santa Barbara, Riess turned to the audience and asked another Nobel laureate, the physicist David Gross, whether this was a tension or a problem. Gross's first answer was cautious. Maybe, he said, you could call it a problem. But by the end of the session, he'd changed his mind. In particle physics, he said, they wouldn't call it a tension or a problem. They'd call it a crisis. And there was one telescope everyone hoped could prove Riess had made a mistake. When the James Webb Space Telescope launched, checking Riess's work was one of its jobs. Here's the specific error everyone expected it to catch. Cepheids live in crowded, dusty neighborhoods, the busy disks of young galaxies. Hubble's camera couldn't always tell one star from its neighbors, so their light bled together. A star that looks brighter than it is also looks closer than it is, exactly the kind of error that could turn a true 67 into an inflated 73. Webb was built to test exactly that. It sits 1.5 million kilometers out, far from Earth's own heat and glare, and its 6.5-meter mirror sees in infrared with a sharpness that makes Hubble's own view look almost blurry by comparison. If crowding was the problem, Webb would expose it instantly. Webb looked, and the tension didn't vanish. A peer-reviewed study of the new data was able to rule out the crowding explanation at more than 8 sigma confidence, a stronger statistical case than the tension itself. Two completely different telescopes, built decades apart, using different instruments and different techniques, and they agree with each other to within 2%. That's the moment this stopped being a hardware problem and stopped being one scientist's outlier result. Riess put it this way once the errors were ruled out. What remained, he said, was, the real and exciting possibility that we have misunderstood the universe. It's not a glitch in a lens, it's a glitch in reality. And the Nobel Prize winner had been right to worry. Something is missing from our best, most trusted model of the universe. So what is it? Let's treat this like an investigation. 3 suspects, and by the end, you'll see why none of them can be fully ruled out. Suspect 1. An invisible particle. Maybe dark energy isn't constant. Maybe it's strengthening or weakening over time. Or maybe there's an entirely new particle at play. Recent data from the Dark Energy Spectroscopic Instrument hints that dark energy might be evolving. It's a real possibility, but still speculative, and it doesn't fully explain why the gap appears so cleanly split between past and present measurements. But if it's true, the stakes go far beyond one disputed number. If dark energy is strengthening over time, the expansion of the universe wouldn't just continue, it would accelerate without limit, eventually tearing apart galaxies, then stars, then planets, then atoms themselves. Cosmologists have a name for that ending: the Big Rip. If dark energy is weakening instead, gravity could eventually win, pulling the entire cosmos back together in reverse. A big crunch. Either way, how this dispute gets resolved doesn't just settle a measurement, it settles how everything ends. Suspect 2. Einstein was wrong, at least on this scale. Here's the uncomfortable one. General relativity has passed every test we've ever thrown at it inside our solar system, but we've never rigorously tested it across the entire observable universe, billions of light years wide. A growing body of published research explores whether gravity itself behaves slightly differently at the largest cosmic scales. Modified versions of Einstein's equations that could shift the expansion rate without needing any new particle or energy at all. If gravity behaves even slightly differently at cosmic scale, the universe our equations describe isn't quite the one we actually live in. Suspect 3. We're standing in an illusion. This is the strangest one. What if there's no error at all, just a trick of geography? One theory proposes that our entire local region, roughly 2 billion light-years across, sits inside an unusually empty patch of space, a Hubble bubble. If we're inside it, the pull of denser matter at its edges could make nearby galaxies look like they're speeding away faster than they really are. In that case, the ancient light from the Big Bang has it right, and the universe we're measuring locally is a distorted version of the real one. Cosmologists don't love this idea because it means we occupy a suspiciously special spot. But it's the one that most literally means this isn't the universe as we assumed it to be. 3 suspects. 3 completely different explanations. And just when it looked like cosmologists were split into 2 clear camps, the data got even messier. In August 2024, a rival team led by Wendy Friedman analyzed Webb's data using different star types and got values hovering right in the middle between 68 and 72. Even scientists looking at the exact same sky with the exact same telescope couldn't agree. Which brings us to Webb's boldest result yet. It's called SN Hope. It's a Type 1a supernova discovered by Webb, gravitationally lensed by a massive galaxy cluster acting like a cosmic magnifying glass. Its light reached Earth along 3 different paths, each arriving with a different delay. By timing those delays, astronomers can calculate the expansion rate without using the traditional distance ladder at all, a completely independent method, and one Riess himself is involved in pushing forward. The preliminary result? About 75, though with a margin of error wide enough that the exact number is still being refined. What it isn't is anywhere near 67. It lands squarely in the local camp, squarely on the side of the warning. If this holds up as the error bars shrink, it's the strongest confirmation yet. The error isn't in our telescopes, It's in our understanding of reality. Whatever the answer turns out to be, this isn't the universe we thought we lived in, and James Webb just proved it.